Bonjour, Algebra 1. Yep, that was French. Yay, me. Hey, Algebra 1, we're going to get started on Lesson 6. You guys just took a quiz over 1 through 5. Lesson 6, we are going to learn how to use our strategies. Okay, we've learned a lot of strategies. We're going to appropriately and efficiently use them to find solutions to basic one variable quadratic equations. We've been doing quadratic equations this whole unit. I call them trinomials. I call them quadratic equations. Anything that has a variable squared in it. Right? We're also going to do a little bit of word problems today. I know I just heard y'all cheer. I heard you cheer through the video. You're so excited. I get it. All right, example 1. Let's see. A physics teacher put a ball at the top of a ramp and let it roll down toward the floor. The class determined that the height of the ball could be represented by the equation h equals negative 16t squared plus 4, where the height h is measured in feet from the ground and time t is measured in seconds. What do you notice about the structure of the quadratic expression in this problem? We know it's quadratic because of that squared right there. What we're missing is what's called the linear term. Oops, not linear team, linear term, which is the x term. That's to the first power, therefore it's linear. So we just have a square and a constant. So in the equation, explain what the 4 represents. If we look at that 4, even if we think a little bit towards linear equations, I know we're not doing linear equations, but now we're looking at the 4, it actually represents the time or the height when time equals 0. Okay, the height when time equals 0, or what we can call the initial height. Moving on. Explain how you would use the equation to determine the time it takes the ball to reach the floor. Well, if we have height equals negative 16t squared plus 4, the time it takes for the ball to reach the floor, well, what's the height at the floor? So if this is what we're looking at, if we know that's 4, what's this height? Well, it's 0. So explain how you use the equation to determine the time it takes for the ball to reach the floor. The ball reaches the floor at height equals 0. So I can actually set that equation equal to 0 and solve for time, right? Now consider the 2 solutions for t. Which one is reasonable? There's actually a few ways we can do this. Okay, few ways we can do this. And I'm actually going to show you those both ways. I usually get a little nervous about showing 2 ways to do things because sometimes it confuses people, but we got this, right? I'm going to isolate that t by moving this forward to the other side of the equal sign. Now I'm going to divide both sides by negative 16, and I have t t squared equals 4 over 16 or 1 over 4. I assume you already had that written down, or you can rewind it and write it down real quick. Now I need to take the square root of both sides. So t equals, whenever you take the square root, you need a positive and a negative answer, 1/2. So t equals positive 1/2 or negative 1/2. Let's see. Well, let's solve it again. We'll talk about what the answer means in a second. I've told you guys quite a few times in class that whenever you have a negative leading number, you need to factor that out. So I'm going to factor out a GCF and get 4t squared minus 1. And then what I've shown you guys is like, hey, now I can get rid of it. Life is grand. I have 4t squared minus 1 equals 0. This actually factors into 2t plus 1, 2t minus 1. That's the a plus b, a minus b that I keep telling you guys about. And now we're going to solve this two binomials by setting them equal to 0. T equals negative 1/2. And then we can go 2t plus, oh nope, minus 1 equals 0. 2t equals 1, t equals 1/2. I got the same answer, I did it two different methods. Okay? So, two solutions for t. Which one is reasonable? Well, I don't know about you, as much as I love to turn back time some days. I've never been able to measure negative time. So for this first solution, I've got t equals 1/2 or negative 1/2. I actually can't have negative time. And here I can't have negative time. So my reasonable answer is 1/2 second, which is super duper short. Yep. Cool. All right, let's read about Lord Byron. Lord Byron is designing a set of square garden plots so some peasant families in his kingdom can grow vegetables. The minimum size for a plot recommended for vegetable gardening is at least 2 meters on each side. Lord Byron has enough space around his castle to make bigger plots. He decides that each side should be the minimum 2 meters plus an additional X meters. What expression can represent the area of one individual garden based on the undecided additional length of X? So what we're saying here is square would be 2 meters times 2 meters, but Lord Byron is feeling really generous. So we actually want to do x plus 2, x plus 2. So our expression, remember an expression doesn't have an equal sign, or x plus 2 squared. All right, there are 12 families in the kingdom who are interested in growing vegetables in the gardens. What equation can represent the total area, A, of the 12 gardens? So now we have A, and this is just one garden, but I need 12, and that is just what I'm going to do right there. Multiply the area times 12. If the total area available for the garden is 300 square meters, what are the dimensions of each garden? So we just said that the area was 12 times x plus 2 quantity squared, but we were just told that that's the total area I have. So let's go ahead and use it. 12x plus 2 squared equals 300 square meters. Dimensions of each garden, I need to figure out what x is to get dimensions. So let's solve for x. Different ways I can solve things. I'm going to go ahead and divide both sides by 12. And I get x plus 2 squared equals 25. Now, this is where we have to use our math skills. We can't just, start doing without thinking. Let's think. When I look at this problem, I see that this number here is a perfect square, and this expression right here is a perfect square, because that's there. So I can actually take the square root of both sides and get just 1x plus 2 equals plus or minus 5, right? So the side length for the garden is 5 because we're going to ignore the negative 5. So we've got 5, positive 5 or negative 5. We're ignoring that one. So a side length, one side length, which we said is this, is equal to 5, right? So that's the dimensions of each garden. So find the value, both values for x that make the equation in part C true for the solution set. Well, I already ignored the negative 5, but if I didn't, this is what I would have. Subtract 2 from both sides, x equals 3. Subtract 2 from both sides, x equals negative 7. Well, again, if x is a dimension that I can measure with a meter stick, I cannot measure a negative 7, but I can measure a 3. So Lord Byron needs to add 3 meters to the minimum measurement of 2 meters. Okay, so we've got our original, which was 2 times 2, and then we made one bigger. So it was x plus 2, but we just solved that x is 5. Cool. Awesome. I've got 4 exercises here, and you have 4 exercises on your sheet. We're going to do some different methods to solve all these, okay? And I'm going to try to show you a pattern. So I'm hoping you see the pattern. Solve each equation. Some of them may have radicals in their solutions. What I see here, I can take a 3 out. It is not the difference of perfect squares yet. What I'm actually going to do, because I just have an x squared here, there's no variable there at all, I'm going to solve this the old-fashioned way. How we first learned how to solve things way, way, way long ago. I'm going to add 9 to both sides. I have 3x squared equals 9. Divide both. I'm isolating the x. And I have x squared equals 3. Square root of both sides. X equals plus or minus square root of 3. My answer. Cool. All right. Here I have x. Well, hold on. I want to show you something with this number 1. If I factored a 3 out, I would have x squared minus 3. Oh, that still doesn't do me any good. Nope. All right. Forget that. Let's just ignore that. I was trying to show a pattern. I couldn't do it. Here, I have a squared and a perfect square. Just like the problem we did with Lord Byron, I can use that information. If I have a square on the left and a perfect square on the left and a perfect square on the right, I can go like this. Take the square root of both sides, and that gives me x minus 3 on the left equals plus or minus 1 on the right. Therefore, I have x minus 3 equals 1, or x minus 3 equals negative 1. Add 3 to both sides. I get x equals 4. Add 3 to both sides, and I get x equals 2. So my answers are 2 or 4. Okay, try this again. Here, I see a square on this side and a perfect square on that side, but that 4 is throwing me off a little bit, so I'm going to move it. So now I have x minus 3 squared equals 1/4. Perfect square on the left, perfect square on the right. X minus 3 equals 1/2, plus or minus. Go ahead and finish solving. X minus 3 equals negative 1/2. Add 3 to both sides. X equals 3.5. Add 3 to both sides. X equals 2.5. And I have 2 solutions. Okay, next, again, the same thing. I've got a 2 over there, which I don't want. And I know I'm going to take the square root of that. So divide both sides by 2 first. X minus 3 squared equals 6. 6 is not a perfect square, but I'm still going for it. I have x minus 3 equals plus or minus the square root of 6. Separate that into 2 problems. And then add 3 to both sides. I can't actually add the 3 to this. Plus 3 plus 3. X equals 3 minus root 6. So I still get 2 answers, right? Now this problem, number 5, says analyze the solutions for exercises 2 through 4. Basically, I did not need to put 1 on here. Notice how the questions all had x minus 3 squared as a factor, but each solution is different. I have a radical, a mixed number, and a whole number. Explain how the structure of each expression affected each problem solution pair. Well, if I look at this first one, or this number 2, I have a perfect square on both sides, which I can just take the square root of both and get all whole numbers. Perfect square, whole numbers. Here, even if I put 1/4 on the right, I've got a perfect square and a perfect square, but my perfect square, this one, is a fraction. So my answer is in fraction. And then here, I'm going to divide that, which gives me 6, which is not a perfect square. So that's a perfect square, that is not, which is what I have a radical answer. Cool? So today we're going to practice, when you get to your problem set, our different skills and how we can use those skills to solve our math problems. And not everyone can be done the same way. You have to make some decisions. Here we are. Peter's a painter, and he wonders if he would have time to catch a paint bucket dropped from his ladder before it hits the ground. He drops the bucket from the top of his 9-foot ladder. That's probably not accurate. We're going to say it's straight up and down. 9 foot. The height h of the bucket during its fall can be represented by the equation h equals negative 16t squared plus 9, where the height is measured in feet from the ground and the time since the bucket was dropped, t, is measured in seconds. How many seconds does the bucket hit the ground? After how many seconds does the bucket hit the ground? Do you think he could catch the bucket before it hits the ground? So when it hits the ground, Our height is 0. And I hope you guys have learned by now, that if there's a negative there, I want to factor it out. So I have negative 16t squared minus 9. That's really a negative 1. I'm going to go ahead and divide both sides by negative 1 because I don't want it there anymore. And I'm running out of space by ladder. We're coming up here. I have 0 equals 16t squared minus 9. Now we can solve this different ways. I'm going this way. I have 9 equals 16t squared. Divide both sides. T squared equals 9/16. Square root of both sides. I have t equals, square root of 9 is 3, square root of 16 is 4, plus or minus 3/4 of a second. Can I have a negative time? Well, no I can't. So our time is 3/4 of a second is when that thing hits the ground. You think Peter's catching that? I don't think Peter could possibly catch that. I think that paint is now on the floor. And that's all we have, isn't it? Sweet. Awesome. 3/4. Good job.